There is a boundary in the history of the universe that no ordinary telescope can cross. It is not a wall in space. It is a moment in time, lying almost 13.8 billion years behind us, when the young cosmos finally became transparent enough for light to travel freely. Before that change, the universe was filled with a hot, dense plasma, light scattered again and again from charged particles, unable to move in a straight path for long. Then the temperature fell. Electrons joined with atomic nuclei. The fog thinned, and a field of radiation began its long journey through expanding space. That radiation is still here. We call it the cosmic microwave background, the oldest light we can observe directly. It reaches us from a universe about 380,000 years old, carrying a faint image of matter before stars, planets, or galaxies had formed. Yet the beginning lies much farther behind it. To move backward from that first visible light is to enter a realm where there are no photographs, no familiar objects, and no surviving beam that can simply be collected by a mirror. The farther back we go, the hotter and denser the universe becomes. Atoms dissolve into nuclei and electrons. Nuclei give way to a sea of more elementary particles. The intervals of time grow smaller until ordinary language begins to lose its grip. Somewhere within that hidden beginning, many cosmologists think the universe passed through a brief phase called inflation. Inflation is not the name of the Big Bang itself. It is a proposed episode of accelerated expansion, usually placed before the hot particle-filled phase described by standard Big Bang cosmology. During this interval, space may have expanded at a staggering rate. Nearby regions were carried apart so quickly that the distance between them could grow faster than light could cross it, without any object locally racing through space beyond the speed of light. No telescope has watched inflation happen. No instrument has detected the field that may have driven it. The idea survives because it offers an elegant explanation for several features of the universe we can observe. Across enormous distances, the cosmos has nearly the same average temperature. On the largest scales, space appears close to geometrically flat. Galaxies are not scattered at random, but trace patterns that seem to have grown from tiny early variations in density. Inflation offers a way for these qualities to share a common origin. In the simplest picture, a region once small enough to be physically connected expanded until it became far larger than the observable universe. Minute fluctuations, perhaps rooted in quantum physics, were stretched across cosmic distances. Much later, gravity drew matter toward the slightly denser regions. Over billions of years, those small differences became clusters, galaxies, stars, and the long branching structure of the cosmos. This picture is powerful, but it is not complete. There are many models of inflation, and no single one has been confirmed. Scientists do not yet know what physical field caused it, how it began, or whether the word before even has a clear meaning at such an early stage. Some predictions match observations well. Others remain beyond present measurement. The oldest visible light gives us clues, but not a final answer. And so this journey begins at the edge of sight. We will follow the evidence backward from the microwave glow that fills the sky toward a time when space itself may have changed its scale. The path will pass through heat, geometry, quantum uncertainty, and the first faint seeds of structure. Beyond the oldest light, the universe does not become empty. It becomes unreadable in a different way. The first visible surface of the universe does not surround us like a shell in any ordinary sense. It appears in every direction because every direction leads backward in time. Wherever a radio telescope looks, it receives radiation released when the cosmos was young enough for matter and light to separate from one another. The source is not a distant place at the edge of space. It is an earlier condition of space itself. For hundreds of thousands of years after the hot beginning, the universe was filled with free electrons, atomic nuclei, and light. Photons could not travel far before striking a charged particle and being redirected. The cosmos was bright, but it was not transparent. It resembled a glowing fog in which no clear image could survive. As expansion continued, the temperature fell to a few thousand degrees. Electrons could then remain bound to nuclei, forming neutral atoms, mostly hydrogen and helium. With far fewer free charges available to scatter them, photons began to move across the universe almost without interruption. That release unfolded over a finite interval, leaving what cosmologists call the surface of last scattering. From our present position, we see it as a background glow stretched across the entire sky. The light began at much shorter wavelength, but the expansion of space lengthened it for almost 14 billion years. Today, it arrives mainly as microwaves, with a temperature just under 3 degrees above absolute zero. It is difficult to sense how faint this is. The radiation carries less warmth than the cold interiors of many laboratory instruments. Yet it is one of the richest records available to science. Embedded within it are tiny differences in temperature, marking places where the early universe contains slightly more or slightly less matter and energy. These differences were the beginning of structure. Regions with a little more matter exerted a little more gravitational pull. Over time, they drew surrounding material inward. Expansion carried large regions apart. From the balance between these processes came filaments, clusters of galaxies, and immense low-density spaces. A map of the microwave background is therefore both an image of infancy and a record of what the mature universe was preparing to become. The glow was recognized in the 1960s when MADE-2 radio engineers working with a large horn-shaped antenna encountered a persistent background signal. It came from every direction. It remained through the seasons. It did not disappear when the equipment was checked and cleaned. The noise was not a defect in the antenna. It was ancient radiation filling space. Later instruments moved above Earth's atmosphere and measured it with increasing precision. They established its near-perfect thermal spectrum, the signature expected from matter and light, once held in close equilibrium. They also revealed that the background is not perfectly smooth. That unevenness matters, but so does the smoothness. Two widely separated regions of the microwave background have almost the same temperature, even though, in a simple, expanding universe model, light would not have had enough time to pass between them before the radiation was released. Without some earlier connection, those distant regions should not have been able to settle into such similar conditions. This is known as the horizon problem. The word horizon refers to a limit set by the distance that information can travel. In the young universe, each region could only be influenced by places close enough for signals to reach it. Regions beyond that horizon should have developed more independently, yet the microwave sky looks strikingly balanced across areas that appear to have been causally disconnected. Inflation offers one possible resolution. Before the rapid expansion, the regions now seen on opposite sides of the sky may have been close together. They could exchange energy and approach a common state. Inflation then stretched that once connected domain until its parts were separated across distances far larger than light could later cross. The similarity we observe would not have been created after the regions moved apart. It would have been inherited from the time when they were still neighbors. There is another clue in the geometry of space. In general relativity, the overall shape of the universe can be described as positively curved, negatively curved, or very close to flat. Curvature on cosmic scales does not mean the universe bends into a visible object outside itself. It describes how lines, angles, and distances behave within space. Observations of the microwave background indicate that the observable universe is very close to spatially flat. Inflation can account for this by stretching any initial curvature across an immense scale. A small portion of a curved surface can appear flat when enlarged enough, just as the ground beneath you seems level even though Earth is round. This is called the flatness problem. The difficulty is not that flat space is impossible. It is explaining why the early universe began so near the special balance required for it to remain nearly flat after billions of years of expansion. Inflation turns that delicate starting condition into a possible consequence of expansion. The most detailed evidence lies in the small temperature variations. Their sizes and distribution are not random. When the microwave sky is analyzed across many angular scales, a pattern appears. It records sound like waves that once moved through the hot plasma. compressing and releasing matter under the competing effects of gravity and radiation. The pattern allows cosmologists to estimate the contents, age, and geometry of the universe. It also places limits on the kinds of fluctuations that could have existed before the plasma formed. Many inflationary models predict fluctuations that are nearly, but not perfectly, the same across different scales. Observations broadly match that expectation. They also show that the early variations followed a comparatively simple statistical pattern. These agreements are among the reasons inflation remains influential. They are not direct photographs of inflation. They do not identify the mechanism that caused it. They do not tell us which proposed field, if any, drove the expansion. The microwave background is more like a shoreline after a tide has withdrawn. Its ripples preserve information about forces that acted earlier, but the water that shaped them is no longer present to be examined in the same way. Every map of this ancient glow is therefore an act of careful inference. The universe gives us a visible surface. Physics asks what hidden history could have left it so smooth, so nearly flat, and yet textured with the small differences from which later structure could grow. Behind that surface, the light does not continue as an image. Only the pattern remains. There is no single agreed picture of what inflation was made of. The word describes a behavior of the universe, not a completed theory of its cause. During an extremely early interval, the scale of space may have increased at an accelerating rate. Inflationary models try to explain how that could happen, what ended it, and how the familiar hot universe emerged afterward. To understand the idea, it helps to leave behind the image of matter exploding outward from a central point. Cosmic expansion is not material rushing through an empty container. It is a change in the distances measured within space. Galaxies now separate because the geometry between large, unbound regions evolves over time. Inflation applies the same general principle to an earlier and far more rapid phase, when no galaxies or stars yet existed, and the contents of the universe were nothing like the matter around us today. In general relativity, expansion is shaped by energy and pressure. Most familiar forms of matter slow cosmic expansion through gravity, but a form of energy with sufficiently negative pressure can produce the opposite behavior. Instead of decelerating, the expansion accelerates. Many models represent this condition with a scalar field. A scalar field assigns a numerical value to every point in space. Temperature in a room offers an everyday comparison, although the proposed inflationary field would not be ordinary heat. Its value could change from place to place, and from one moment to another, carrying energy even where there were no particles. Physicists often call this hypothetical field the inflaton. The name is convenient, but it should not be mistaken for a detected substance. No experiment has yet identified an inflaton particle, and different models give the field different properties. The behavior of the field is often pictured through an energy landscape. Imagine a smooth slope. The position of the field on that slope determines how much potential energy fills space. If the field changes only gradually, its potential energy can remain nearly constant while the universe expands. In the equations of general relativity, that nearly constant energy density can drive accelerated expansion. The field is not a ball rolling across a literal surface. The landscape is only a mathematical way of describing how its energy changes. While inflation continues, the amount of energy in each small region remains almost unchanged even as space grows. New volume appears, and each new part carries nearly the same field energy. The total energy associated with the field can therefore increase with the expanding volume, a result that feels unfamiliar when compared with objects in daily life. General relativity does not require the universe as a whole to obey the conservation rule used for an isolated box in unchanging space. In a dynamic cosmos, energy accounting is tied to the evolving geometry itself. The speed of this growth is usually described through the scale factor, a quantity that tracks how distances between points carried with the expansion change over time. During ordinary radiation or matter-dominated expansion, the scale factor grows according to a power of time. During idealized inflation, it grows almost exponentially, equal Intervals of time produce repeated multiplication rather than repeated addition. Cosmologists often measure the duration of inflation in e-folds. One e-fold means that the scale factor has increased by the mathematical constant called e, a little less than 3. 2 e-folds multiply it again. After 60 e-folds, the increase is immense. The exact number required depends on the model and on what happened after inflation. A commonly discussed range is around several dozen e-folds, enough to stretch a once connected region beyond the size of the observable universe. This expansion does not mean that matter moved locally through space faster than light. Relativity limits the speed at which an object or signal passes nearby through space-time. It does not impose the same limit on how quickly the metric distance between sufficiently separated regions can grow as space expands. During inflation, 2 locations could be carried apart so rapidly that light emitted from one would never reach the other, while the accelerated phase continued. Each local observer would still measure nearby light, traveling at the usual speed. This distinction is one of the reasons the phrase "faster than light" can mislead. Nothing nearby needs to outrun a photon. The geometry changes beneath the journey. Inflation cannot continue forever in the part of the universe that became our observable cosmos. At some point, the condition driving accelerated expansion had to weaken. In many models, the inflaton field moves toward a lower energy state. Its nearly constant potential energy begins to change more quickly. The negative pressure behavior ends, and the rapid acceleration stops. The energy stored in the field must then be transferred into other forms. This transition is called reheating. The name does not imply that a previously cold universe was warmed by an outside source. It refers to the conversion of the field's energy into a hot mixture of particles and radiation. Through interactions that remain model-dependent, the energy driving inflation may have produced the ingredients of the hot Big Bang phase. From that point onward, the universe would continue to expand, but more slowly. It would be filled with an intensely energetic plasma. As temperatures fell, particle reactions changed. Quarks became bound inside protons and neutrons. Light nuclei formed during the first minutes. Much later, electrons joined those nuclei, and the microwave background began its long passage through transparent space. In this view, inflation is not a rival to the hot Big Bang. It is a proposed prelude that sets the initial conditions for it. The phrase Big Bang has often been used for the entire early history, which can blur the distinction. Modern cosmology describes the hot Big Bang with considerable observational support, beginning from an early hot, dense, expanding state. Inflation is an attempt to explain why that state possessed the particular smoothness and small irregularities seen in later evidence. What happened before inflation is even less certain. Some mathematical solutions allow inflation to begin after an earlier phase. Others suggest that inflation may continue eternally in some regions, ending only in separate domains. Still others replace the inflationary picture with a bounce, a contracting phase, or a different mechanism for generating early structure. At present, these possibilities are not equal in detail, but none gives us a directly observed account of an absolute beginning. Even time itself becomes difficult to discuss near this boundary. In everyday speech, asking what came before seems natural. In cosmology, the question depends on whether a theory extends time smoothly through the relevant regime. If space-time emerged from a quantum process, the ordinary meaning of before may no longer apply. Inflation does not settle that question. It can describe a universe already equipped with space-time, a field, and physical laws. It may push our explanation closer to an earlier boundary while leaving the origin of those ingredients untouched. This is not a failure unique to cosmology. Every successful theory has a domain where its tested descriptions end. Newtonian gravity gives way to relativity under stronger conditions. Classical physics gives way to quantum mechanics at small scales. Inflation may be part of a deeper framework that has not yet been found. The challenge is that the energies associated with the earliest universe are far beyond those produced by current accelerators. Scientists cannot recreate inflation as a whole in a laboratory. They search instead for consequences that may have survived. The microwave background carries one set of clues. The distribution of galaxies carries another. Certain models also predict a background of primordial gravitational waves, subtle distortions in spacetime generated during inflation. If those waves left a distinctive imprint in the polarization of the microwave background, the pattern could provide evidence about the energy scale of inflation. Searchers have placed increasing strong limits on such a signal, but no primordial detection has been confirmed. This absence does not eliminate inflation, but it constrains some versions more strongly than others. The theory, therefore, occupies an unusual place. It is more than a loose idea, because it has produced quantitative predictions that observations can test. Yet it is less than a completed account, because the physical driver remains unknown and many models can fit the data. The earliest universe is approached through this narrow passage between confidence and uncertainty. We know that the cosmos expanded from a hotter, denser condition. We know that its oldest visible radiation is remarkably uniform and carries a precise spectrum of small variations. We know that large-scale structure grew from early differences in density. Inflation connects these facts through a possible episode of accelerated expansion. But the connection is still being tested. Beneath the equations lies a simple transformation. A region too small to contain any star, planet, or atom may have been stretched until it held everything we can now observe. Energy in a field may have become a hot sea of particles. Microscopic uncertainty may have been carried outward until it shaped the positions of galaxies. The next part of the story begins within those tiny uncertainties, before gravity had stars to gather, and before matter had settled into any familiar form. A universe made perfectly smooth would have remained almost empty of structure. Gravity can deepen an existing difference, but it cannot gather matter toward a place that is no denser than anywhere else. If every region began with exactly the same density, then every direction would pull with the same strength. There would be expansion and cooling, but no preferred locations for clouds to form, and no clear path toward galaxies. The visible universe is not like that. Even at the time recorded in the cosmic microwave background, some regions were slightly denser and others slightly thinner. The differences were tiny, but they were enough. Gravity had something to work with. Inflation offers an account of where those first differences may have come from. The proposed inflaton field would not have been perfectly still. In quantum physics, a field cannot remain fixed at one exact value with no variation at all. At small scales, it fluctuates. These fluctuations are not ordinary vibrations moving through a material substance. They belong to the probabilistic behavior of quantum fields themselves. In a laboratory, quantum fluctuations remain microscopic. They influence atoms, particles, and forces far below direct human perception. During inflation, the expansion of space may have changed their role. A fluctuation that began across a very small region could be stretched as that region expanded. Its wavelength would grow with the scale of the universe. What began in a quantum regime could be carried outward until it extended across distances that would later contain clusters of galaxies. This is one of the most unusual ideas in modern cosmology. The largest structures we see may have grown from variations that began at the smallest scales. Imagine a pattern of ripples with many wavelengths. During inflation, every wavelength is stretched. At first, a given ripple lies within a region where physical influences can cross from one side to the other. Later, expansion carries it beyond the distance light can travel during that phase. Cosmologists describe this as a mode crossing the horizon. Nothing passes through a visible edge. The relevant scale simply grows larger than the region within which local interactions can keep different parts in contact. Once stretched beyond that scale, the fluctuation no longer evolves in the same way. Its amplitude can become nearly fixed. Expansion preserves the pattern while enlarging it. After inflation ends, the horizon grows differently. Over time, those stretched modes come back within causal reach. By then, they are no longer merely microscopic quantum variations. They have become broad differences in density and curvature spread through the young universe. The denser regions do not immediately collapse. The cosmos is still hot, and radiation pushes against compression. Matter and light move together in a plasma. Gravity pulls material inward, while pressure drives it outward, creating waves through the early mixture. Those waves later leave their signature in the microwave background. The warmer and cooler patches on a microwave map are not simple photographs of dense and empty places. Their meaning depends on motion, gravity, temperature, and the way photons climbed through gravitational fields before beginning their journey toward us. Still, the full statistical pattern carries information about the original fluctuations. Scientists do not focus on one bright patch and ask what object it became. The early universe was not mapped into individual future galaxies in such a direct way. Instead, they measure how much variation appears at different scales across the sky. This is called the power spectrum. It tells us how fluctuations' strength changes with wavelength and whether the overall pattern resembles the one expected from simple inflationary models. One important feature is near-scale invariance. A perfectly scale invariant spectrum would give fluctuations a particular balance across a wide range of sizes. The observed pattern is close to that form, but not exact. There is a slight tilt with somewhat different strength at smaller scales than at larger ones. That small departure matters. Many models predict such a tilt because the field driving inflation would not remain in precisely the same condition from one moment to the next. As the field changed, fluctuations leaving the horizon at different times would acquire slightly different strengths. Measurements of the microwave background have found a spectral pattern broadly consistent with this expectation. The fluctuations also appear close to Gaussian. A Gaussian distribution is a familiar bell-shaped statistical pattern. Most variations remain near the average, while larger departures become less common. Inflationary models with a single slowly changing field often produce fluctuations of this kind. Researchers search for subtle departures called non-Gaussianity. A clear detection could reveal interactions in the early universe or point toward more complicated physics. So far, observations have not found strong primordial non-Gaussianity. The early pattern remains comparatively simple. Another feature concerns the relationship among different kinds of matter and radiation. The observed fluctuations are largely adiabatic. This means that the components of the early universe varied together in a coordinated way. A slightly denser region was not created by moving one substance into it while removing another in equal measure. Instead, the total density changed while the relative mixture stayed nearly uniform. Simple inflationary scenarios naturally generate this kind of initial condition. Together, near-scale invariance, near-Gaussianity, and adiabatic fluctuations form a notable agreement between theory and observation. They do not prove that inflation occurred. Other mechanisms may imitate some of the same signatures, but any competing account must explain why the early universe carries this particular combination. Their challenge is that inflation is flexible. Different choices for the field, its energy landscape, and its interactions can produce different predictions. Some models are disfavored because they would create fluctuations or gravitational waves larger than observations allow. Others remain compatible with present data. As measurements improve, the space of possible models narrows. This is how the earliest fraction of cosmic history becomes testable. Not by seeing it directly, but by comparing predicted statistical traces with patterns preserved in ancient radiation and large-scale structure. A person beneath a clear sky sees none of this arrangement. The stars appear as separate points. The Milky Way may form a pale band. Galaxies beyond our own remain hidden without instruments. Yet every visible concentration of matter belongs to a pattern that began long before the first source of starlight. The carbon in a resting hand was made inside stars. Those stars formed inside galaxies. The galaxies gathered within dark matter halos. The halos emerged from early density differences, and those differences may lead back to quantum fields in an inflationary universe. The connection is physical, written through gravity across many levels of scale. A tiny initial excess of matter grows slowly. At first, radiation resists it. Later, as the universe cools and matter becomes more influential, gravity gains time to deepen the contrast. Dark matter, which does not interact with light in the same way ordinary matter does, begins to collect into an invisible framework. Ordinary gas falls toward these gravitational wells. It compresses, cools, and eventually forms the first stars. Groups of stars assemble into young galaxies. Galaxies merge and gather along filaments. Empty regions become emptier as matter flows toward growing structure. The process requires billions of years, but its initial information is present from the beginning. Modern galaxy surveys map that later structure over immense volumes. They show walls, threads, knots, and voids, forming what is often called the cosmic web. The web is not a frozen imprint of quantum fluctuations. Gravity has reshaped it, non-linear processes have complicated it, and expansion has altered its growth. Yet its broad statistical properties remain linked to the primordial pattern. By comparing the microwave background with galaxy distributions, gravitational lensing, and other observations, cosmologists test whether one set of early conditions can explain many later forms. The agreement is strong across a wide range of scales, though puzzles remain. Measurements made using the early universe and measurements made in the nearby, mature universe do not always align perfectly. Some differences may come from systematic errors. Others may point toward missing physics. Their meaning is still debated. Inflation itself is not protected from revision. A theory earns confidence by surviving attempts to distinguish it from alternatives. It must make predictions narrow enough that evidence can rule something out. If every possible observation can be matched by some version of a theory, then the theory becomes difficult to test as a whole. For this reason, physicists do not ask only whether an inflationary model can fit the data. They ask which models remain economical, which require fine adjustment, and which make distinctive predictions for future measurements. One of the most sought-after predictions involves primordial gravitational waves. Quantum fluctuations would not affect only the field responsible for density differences. Spacetime itself could fluctuate. Inflation might stretch those tensor variations into a background of gravitational waves surrounding the universe. They would be far too faint to hear with present ground-based detectors. Their clearest accessible trace may be a curling pattern in the polarization of the cosmic microwave background, known as primordial B modes. A confirmed detection would open a new line of sight into inflation. Its strength could reveal information about the energy scale of the expansion and rule out many models at once. But the search is difficult. Dust within the Milky Way can create polarized microwave emission that resembles the desired pattern. Gravitational lensing can also convert other polarization signals into B modes. Instruments must observe at several frequencies, map the foregrounds, and separate a possible primordial trace from everything between us and the ancient sky. No primordial B-mode signal has yet been confirmed. That absence is informative. It places upper limits on the strength of inflationary gravitational waves and excludes some once popular versions of the theory. The remaining possibilities predict weaker signals, or none large enough for current instruments to find. The earliest universe therefore becomes clearer by subtraction. One model leaves too much tilt, another produces excessive non-Gaussianity. Another predicts gravitational waves that are not seen. Possibility after possibility is compared with a sky whose faint variations have crossed nearly the full age of the cosmos. What remains is not a single final picture, but a smaller landscape of explanations. In that landscape, quantum uncertainty is not merely noise. It becomes the possible source of cosmic form. The first galaxies did not need to be planned in advance. They required only a pattern of slight differences, expansion to preserve and enlarge those differences, and gravity with enough time to follow them. From fluctuations too small to picture came distances too large to cross, and between those scales, the universe learned how to gather. The end of inflation would not have looked like an explosion into empty space. There was no outside region waiting to receive the universe. Space itself had already been expanding, and the energy that sustained that expansion was spread through it. What changed was the form that energy took. In many models, the field responsible for inflation gradually lost the condition that kept its energy nearly constant. The accelerated expansion slowed. The field began to move more rapidly toward a lower energy state, and then to oscillate around it. Those oscillations could transfer energy into other quantum fields. The process is called reheating, but the word can suggest a simpler event than the physics allows. Inflation may have left the universe in a state dominated by a smooth field, with very few ordinary particles. Reheating describes the conversion of that field energy into a dense population of particles and radiation. The details are not known. The inflaton, if it existed, may have decayed gradually. In some models, its oscillations could have driven a rapid and highly efficient stage called preheating, creating particles in bursts through quantum effects. Those particles would then interact, scatter, and approach a thermal distribution. Only after this exchange would the universe resemble the hot, dense beginning usually associated with the Big Bang. The temperature reached during reheating remains uncertain. It depends on the energy scale of inflation, the properties of the field, and the strength of its interactions with other forms of matter. Some models allow temperatures far beyond anything produced in a laboratory. Others end inflation at lower energies. This uncertainty matters because the conditions after reheating determine which particles could exist and which physical processes could occur. At extreme temperatures, the distinctions familiar in the present universe may not yet have applied in the same way. Forces that now appear different may have behaved as parts of a more unified description. Fields that currently possess stable ground states may have occupied different configurations. As the universe expanded, it cooled. Transitions occurred, not because the cosmos moved through layers of surrounding space, but because the average energy of its particles fell. In a cooling material, water can freeze or a magnet can acquire an ordered direction. In the early universe, changes in field states may likewise have altered the behavior of particles and forces. These cosmic phase transitions belong to particle physics rather than weather or chemistry, but the general idea is related. The same underlying system can display different properties at different energies. Some proposed transitions may have created defects or gravitational wave backgrounds. No confirmed observation has yet identified such a relic from the inflationary aftermath. The possibilities remain active targets for theory and experiment. One transition that can be described within established particle physics concerns the electroweak interaction. At sufficiently high energies, electromagnetism and the weak nuclear force are represented within a unified framework. As the universe cooled, the Higgs field settled into the state associated with its present value. Particles interacting with that field then behaved as particles with mass, while the photon remained massless. This did not give all matter its mass in one simple act. Much of the mass of protons and neutrons comes from the energy of the strong interaction binding quarks and gluons. Still, the electroweak transition helped establish the particle properties that would shape later matter. A deeper puzzle was also present. The hot early universe should have produced matter and antimatter in nearly balanced amounts. When a particle meets its antiparticle, the pair can annihilate into radiation. If the balance had remained exact, almost all matter would have disappeared, leaving a cosmos filled mainly with light. That is not the universe we inhabit. For roughly every billion pairs of matter and antimatter that vanished, a small excess of matter appears to have remained. That slight imbalance was enough to build every galaxy, cloud, ocean, and living body that came later. The origin of the imbalance is called baryogenesis. Physics contains several ideas for how it might have happened, but no complete mechanism has been confirmed. Any successful account must allow processes that distinguish matter from antimatter, depart from perfect thermal balance, and change the net number of particles, such as protons and neutrons. Inflation may influence when or how such conditions arose, but inflation alone does not explain the asymmetry. The question belongs to the uncertain bridge between the smooth inflationary phase and the particle-filled universe. As expansion continued, the cosmos entered a state often described as a quark-gluon plasma. Quarks, the constituents that later become bound inside protons and neutrons, moved through a dense environment with gluons, the carriers of the strong interaction. Temperatures were too high for stable protons and neutrons to persist. Laboratories have briefly recreated quark-gluon plasma in collisions between heavy atomic nuclei. These experiments do not reproduce the entire early universe, but they allow physicists to study matter under conditions where quarks and gluons are not confined within individual particles in the ordinary way. Within the first small fraction of a second, further cooling changed the balance. Quarks became confined into composite particles called hadrons. Among them were protons and neutrons. Antimatter versions formed as well, and most of the remaining pairs annihilated. The slight matter surplus endured. The universe was still far too hot for atoms. It was filled with radiation, neutrinos, electrons, positrons, protons, neutrons, and other particles interacting in rapid succession. At around 1 second, neutrinos stopped interacting frequently enough to remain in thermal contact with the rest of the plasma. They began traveling almost freely through space. A background of these primordial neutrinos should still fulfill the universe today, older than the microwave background by hundreds of thousands of years. It has not been detected directly. Its expected influence is woven into cosmological calculations, and observations are consistent with its presence, but measuring the particles themselves is an immense technical challenge. If such a detection becomes possible, it would offer information from a time when light was still trapped in the plasma. Gravity may carry an even earlier record. Gravitational waves interact weakly with matter and could have moved freely through epochs, opaque to photon. A primordial gravitational wave background might contain traces of inflation, reheating, or later phase transitions. For now, this earlier universe remains known mainly through consequences. A few seconds after the hot phase began, protons and neutrons were present, but the temperature remained high enough to break apart most nuclei as soon as they formed. Expansion continued to lower the energy of the radiation. After several minutes, conditions allowed a brief period of primordial nucleosynthesis. Protons and neutrons joined into light atomic nuclei. Most protons remained alone and would later become the nuclei of hydrogen atoms. A substantial fraction of the available neutrons became bound into helium nuclei. Small amounts of deuterium, helium-3, and lithium also formed. The process ended as the universe became too cool and thin for nuclear reactions to continue efficiently. The predicted abundances of these light elements provide one of the strongest lines of evidence for the hot Big Bang. When astronomers measure ancient gas and low metallicity environments, the broad pattern agrees with calculations based on an expanding universe that passed through this early nuclear phase. Heavier elements could not be built in large quantities under those conditions. Carbon, oxygen, silicon, iron, and the other elements familiar on Earth would require stars, stellar explosions, and later collisions. The early universe supplied mostly hydrogen and helium. It also supplied time. For hundreds of thousands of years after nucleosynthesis, the cosmos remained a plasma. Atomic nuclei moved among free electrons. Photons scattered continuously and could not preserve a clear path. Expansion kept stretching their wavelengths and reducing their energy. The temperature declined until electrons could remain attached to nuclei. Neutral atoms became common, scattering dropped sharply, and the oldest directly visible light was released. The cosmic, not the first light that existed. Photons, not the first light that long before it. It is the oldest light that could begin a journey and continue largely undisturbed until reaching us. This distinction changes the meaning of visibility. The universe did not suddenly turn on at 380,000 years. It became transparent. Before that transparency, events still occurred. Particles formed and vanished. Forces changed behavior. Matter gained its slight advantage over antimatter. Nuclei assembled. Neutrinos departed from the thermal mixture. perhaps gravitational waves were generated by processes that have left no other accessible trace. The first visible image arrives after much of the foundation has already been laid. Seen this way, inflation stands at the beginning of a long conversion. A field-dominated cosmos becomes a thermal sea. The thermal sea separates into particle species. Quarks become bound. Matter survives annihilation by a narrow margin. Nuclei form, and eventually electrons settle around them. Each stage preserves something from the one before while opening a new range of possible structure. The chain is supported unevenly. Nucleosynthesis and the microwave background are tied closely to observation. The quark-gluon phase is supported by established physics and laboratory evidence at high energies. The earliest transitions, baryogenesis, reheating, and inflation itself, carry larger uncertainties. Cosmology does not hide those differences. It uses them to mark where knowledge is firm and where new evidence is needed. The equations can follow the universe backward through many stages, but the confidence of the description changes as the path retreats. Near the microwave background, measurements are abundant. Near the first few minutes, light element abundances provide a strong test. Earlier still, particle theory guides the reconstruction. At reheating, the number of plausible histories widens, and before inflation, the map may no longer be a map at all. Yet every stage leaves the next one with something to inherit. The present universe inherited its matter from an imbalance no one has fully explained. It inherited its light elements from a nuclear interval lasting only minutes. It inherited its large-scale pattern from fluctuations that may have crossed the horizon during inflation. Nothing familiar existed then, but the conditions for familiarity were accumulating. The universe had not yet made a start. It was already preparing the materials from which starlight would come. Beyond reheating, the path backward begins to divide. The hot early universe is supported by several independent lines of evidence. Inflation reaches farther into uncertainty, offering a compelling explanation for the smoothness, geometry, and initial structure of the cosmos. But inflation is not the only framework physicists have explored. Any alternative must do more than describe an early universe that seems possible. It must explain why distant regions share nearly the same temperature, why space appears so close to flat, and why primordial fluctuations have the particular statistical properties observed in the microwave background. It must also connect with the successful history that follows. Light nuclei still need to form in the correct proportions. The universe must become transparent at the right stage. Matter must gather into the large-scale structures astronomers now map. A new theory cannot simply replace inflation at the beginning while disturbing everything that works afterward. This makes the early universe a difficult place for alternatives. One family of ideas replaces an initial expansion with an earlier period of contraction. In these models, the universe may have existed before the hot phase in a larger, colder state. It then contracted, becoming denser and hotter, before passing through a bounce and expanding again. The bounce would take the place of an absolute beginning, at least within the mathematical description. Time could extend through the transition, connecting an earlier cosmic phase with the one we inhabit. Ordinary general relativity does not make such a passage easy. As matter contracts, density and curvature tend to increase. Following the equations backward can lead toward a singularity, where familiar descriptions break down. A successful bounce, therefore, requires new physics. Quantum gravity might alter the behavior of space-time at extreme density. Unfamiliar forms of matter or energy might resist collapse. The geometry itself could change in ways not captured by classical relativity. Several approaches attempt to provide such a mechanism, but none has been experimentally confirmed. A related proposal is the ekpyrotic universe. Its name comes from an ancient word associated with cosmic fire. In modern theory, it describes a period of very slow contraction driven by a field with unusual properties. This contraction, irregularities in curvature, and certain forms of disorder may become less important, leaving the universe smooth and flat before a transition into expansion. The mechanism differs sharply from inflation. Inflation smooths the cosmos through rapid accelerated growth. Ekpyrotic models attempt to reach a similar result through controlled contraction. Both can, under certain conditions, generate primordial fluctuations, but the detailed predictions differ. Simple ekpyrotic models do not naturally produce the observed density pattern in the same way as simple inflation. Additional fields or conversion mechanisms are often needed. These additions may create distinctive forms of non-Gaussianity or gravitational wave behavior that future observations could test. Another possibility is a cyclic universe. In a cyclic picture, cosmic history may contain repeated phases of expansion and contraction. Each cycle could begin with a bounce and end after an immense period of evolution. The idea carries a natural appeal because it removes a unique first moment. The universe would not emerge from a boundary beyond explanation. It would pass through recurring transformations. Yet repetition on cosmic scales creates its own problems. Entropy tends to increase. Stars burn fuel, black holes grow, and usable energy becomes more dispersed. A cycle that simply repeats would inherit the disorder of the one before it. Over many cycles, the accumulation could prevent the universe from returning to the same conditions. Cyclic models therefore need a way to dilute, remove, or reinterpret entropy. Some rely on enormous expansion between cycles. Others propose that only certain physical quantities continue through the transition. These remain active theoretical questions rather than established cosmic history. There are also models in which the universe begins in an almost static state. An emergent universe may exist for an indefinite period in a stable or slowly evolving condition before entering expansion. In such a framework, there may be no initial singularity and no earlier contraction. The hot universe grows out of a long-lived precursor state. Maintaining that state is difficult. Small disturbances can make a static cosmos unstable, causing it either to collapse or expand too soon. The required fields and initial conditions may themselves demand explanation. Quantum cosmology approaches the question from a different direction. General relativity treats space-time as a smooth geometry. Quantum theory describes physical systems through probabilities, states, and fluctuations. Near the beginning, where density and curvature may become extreme, both descriptions should matter at once. A complete theory of quantum gravity would be needed. No such theory has yet been confirmed. Several research programs attempt to build one, including approaches based on quantized geometry, higher dimensional objects, or new mathematical relationships among fields and spacetime. In quantum cosmology, the universe may not begin as a classical space, evolving through an ordinary clock. Some proposals describe a quantum state from which familiar spacetime emerges. Others use a geometry that becomes more like a spatial direction near the earliest boundary, making the question of what happened before resemble asking what lies north of the North Pole. This comparison is useful only to a point. The mathematics is more precise than the image, and different models give different meanings to the beginning. One well-known proposal removes a sharp initial edge by allowing the geometry of the earliest universe to close smoothly. Time, as experienced later, would emerge from a region where the distinction between time and space behaves differently. Another approach describes the universe as appearing through a quantum tunneling event. Quantum tunneling allows a system to cross a barrier it could not pass under classical physics. Applied to cosmology, it may describe the emergence of an expanding universe from a state without ordinary classical spacetime. The word nothing often appears in discussions of such models, but it can be misleading. A quantum state governed by equations, boundary conditions, and possible geometries is not necessarily the philosophical absence of everything. Physics can describe the transition from one formal state to another. It does not automatically explain why laws or mathematical possibilities exist at all. The boundary between physical and philosophical questions becomes easy to blur here. Cosmology can ask whether time extends through an earlier phase. It can calculate how fluctuations evolve. It can compare a model's predictions with observations. It may not be able to determine why there is a universe rather than no universe. because that question may not translate into a testable physical model. Inflation does not avoid all of these difficulties. Even if inflation occurred, it may require an explanation for its initial conditions. The inflaton field must begin in a suitable state. A region must possess enough smoothness for accelerated expansion to start. Some models make this beginning easier than others, but the question does not disappear entirely. Inflation can also lead to eternal inflation. In many versions, the field does not finish inflating everywhere at the same time. Quantum fluctuations may cause some regions to remain in the inflationary state while others exit and become hot expanding universes. The inflating regions continue producing more volume. Within them, additional regions stop inflating, each potentially developing into a domain with its own later history. This process can continue without ending globally, even though inflation ended in the region that became our observable universe. The resulting picture is sometimes described as a multiverse. The term covers several different ideas and should be used carefully. In the inflationary context, it may refer to many causally separated regions created by an eternally inflating background. These domains are not necessarily separate universes in every philosophical sense. They may be parts of a larger spacetime that can no longer exchange signals. Some theories suggest that different domains could settle into different low-energy physical states, giving them different particle properties or effective constants. Others produce domains that are more alike. There is no direct observational confirmation that such regions exist. If they are permanently beyond our causal horizon, testing them becomes difficult. Researchers have considered whether collisions between expanding domains might leave patterns in the microwave background, but no convincing signature has been established. Eternal inflation may arise naturally in some models, yet its predictions can be hard to define. When infinitely many regions and events are possible, calculating probabilities requires a rule for comparing infinities. Different rules can produce different answers. This is known as the measure problem. It is not a minor technical inconvenience. It affects whether eternal inflation can make clear statistical predictions about what observers should expect to see. These complications do not mean the idea is wrong. They show that extending inflation beyond the observable domain introduced questions different from those addressed by the microwave background. Within our own observable region, inflation can be tested through its traces. Beyond that region, the theory may become much harder to distinguish from speculation. This is why scientists often separate inflation as an early mechanism from broader claims about a multiverse. The first can be constrained by measurements of primordial fluctuations, spatial curvature, and gravitational waves. The second may depend on features of the theory that remain inaccessible. The universe does not reveal every scale with equal generosity. Atoms can be studied in laboratories. Stars can be observed across their life cycles by looking at many stars of different ages. Galaxies can be mapped through most of cosmic history. The earliest universe offers only relics, a thermal glow, a distribution of matter, light element abundances, possible backgrounds of neutrinos and gravitational waves. Each relic carries information forward, but each has been altered by later processes. The task is to identify which early histories could have produced the same surviving evidence. Inflation remains the leading framework because it connects many observations through a relatively simple physical idea. Its alternatives are valuable because they reveal which successes are unique to inflation and which might arise in other ways. A contracting universe may also become smooth. A bounce may replace a singularity. Quantum geometry may change the meaning of the beginning. A longer theory may contain inflation without making it the first event. None of these possibilities is established merely because equations allow it. Their value comes from the predictions they produce and the possibility that nature may choose among them through evidence. The uncertainty is not an empty space where every idea is equally likely. It has shape. Some models fail because they generate the wrong spectrum of fluctuations. Some are unstable. Some require conditions as carefully arranged as the ones they were designed to explain. Some survive because current observations are not yet precise enough to separate them. The boundary keeps moving as measurements improve. What once seemed beyond science can become a question of polarization, curvature, or statistical correlation. A theoretical difference hidden near the beginning may leave a faint trace across the microwave sky. The past cannot be visited, but it can sometimes be narrowed. And at the farthest edge of that narrowing, several possible universes still wait behind the same ancient light. The earliest universe may be hidden from direct sight, but it is not beyond measurement. Every surviving trace places limits on what could have happened before the first atoms formed. A model of inflation, a contracting phase, or a quantum beginning must eventually enter the later universe we observe. It must leave behind the right geometry, the right fluctuations, and the right sequence of thermal events. This makes the sky a testing ground for physics at energies no human instrument can reproduce. The most familiar record is the cosmic microwave background, but even this ancient light contains information that has not yet been fully extracted. Its temperature has been mapped with remarkable precision. Its polarization offers another layer. Light can be polarized when its electric field develops a preferred orientation. In the early plasma, photons scattered from free electrons. Where the surrounding radiation had the right kind of uneven pattern, that scattering produced polarization across the sky. Most of the resulting signal forms what cosmologists call E-modes. Their pattern resembles radiating or circular arrangements rather than curls. E-mode polarization has been measured and agrees well with the broader picture of an expanding universe shaped by primordial fluctuations. B-modes are different. They form a curling pattern that can arise in more than one way. The gravity of intervening matter bends the paths of microwave photons, distorting some E-modes into B-modes. This lensing signal has been detected and can be used to map the otherwise invisible distribution of matter. A second kind of B-mode may have been produced by gravitational waves from inflation. If spacetime carried tensor fluctuations during the accelerated expansion, those waves could have left a particular polarization pattern on large angular scales. The pattern would be extremely faint, and it would lie beneath several layers of foreground emission. Dust grains within the Milky Way align partly with the galaxy's magnetic field. Their thermal radiation is polarized. Electrons moving through magnetic fields produce additional emission. Both can imitate parts of the primordial signal. The sky must therefore be measured at many frequencies. A genuine cosmological pattern would have one frequency dependence. Galactic dust and other foregrounds would have others. By observing the same region in several microwave bands, researchers can build models of the intervening material and gradually separate it from the background. Even then, certainty requires care. An apparent signal may depend on how the foreground is modeled. Instrumental effects can introduce false patterns. A telescope's beam, calibration, and detector behavior must be understood with precision. Independent instruments must examine overlapping regions of sky. This is why a single dramatic announcement cannot settle the question. The search proceeds through repeated observation, comparison, correction, and stricter limits. Each non-detection removes some possible inflationary energy scales. Each improvement in sensitivity narrows the class of models that can remain. A primordial B-mode detection would not tell us everything about inflation. Several models could produce similar amplitudes, but it would show that gravitational waves existed in the earliest accessible era, and it would connect quantum behavior with the geometry of space-time across cosmic distances. There are other signatures to seek. The statistical pattern of primordial fluctuations may contain tiny deviations from Gaussianity. A simple inflationary field with weak interactions tends to produce a nearly Gaussian distribution. Multiple fields, sharp changes in the inflationary energy landscape, or stronger interactions can create more complicated correlations. These correlations are not visible as one unusual spot sky. They appear through relationships among many points and many scales. Researchers measure 2-point, 3-point, and higher order correlations. The names describe how many locations are compared at once. A 2-point function helps construct the familiar power spectrum. A 3-point function, often expressed through a bispectrum, searches for patterns that a purely Gaussian field would not produce. Different early universe mechanisms can generate different shapes in these correlations. One pattern may be strongest when 3 wavelengths are similar. Another may become clear when one wavelength is much longer than the other 2. These configurations can reveal whether the fluctuations came from one slowly evolving field, several coupled fields, or a phase with different dynamics. So far, measurements have found no strong primordial non-Gaussianity. That result supports simpler inflationary pictures and limits many alternatives, though the remaining range is still broad. Future surveys may detect smaller effects or tighten the constraints until entire families of models become untenable. The distribution of galaxies adds a much larger 3-dimensional record. The microwave background provides a mostly 2-dimensional view of an early surface. Galaxy surveys measure positions across distance as well as direction, mapping the later universe through volumes containing millions of galaxies. Those galaxies do not preserve the primordial field in a simple form. Gravity has moved matter, galaxies have merged, stars have formed, and energetic processes have changed the visible gas. Yet, statistical reconstruction can recover information about the original pattern. On very large scales, matter still traces the early fluctuations. A subtle feature known as baryon acoustic oscillations appears in the distribution of galaxies. It is the later imprint of pressure waves that traveled through the hot plasma before atoms formed. When the photons were released, those waves stopped propagating in the same way, leaving a preferred separation scale in the matter pattern. That scale acts as a cosmic ruler. By observing how its apparent size changes with distance, astronomers measure the expansion history of the universe. The same data also test the geometry and growth of structure expected from early conditions. Future surveys will map broader regions and fainter galaxies, improving sensitivity to subtle departures from standard predictions. They may reveal features in the primordial spectrum that a smooth inflationary model would not create. A brief change in the speed of the inflaton field could leave oscillations across certain scales. A step or bend in its energy landscape might produce a localized feature. A second field could add a correlated pattern. The absence of such features would also matter. It would favor models in which inflation unfolded with fewer interruptions and weaker interactions. Another record lies in neutral hydrogen. Before the first stars fully transformed their surroundings, most ordinary matter existed as hydrogen gas. The atom has a natural radio transition with a wavelength of 21 centimeters. Expansion stretched this signal to longer wavelengths, depending on when it was emitted or absorbed. Mapping the 21-centimeter background could reveal an enormous volume of the young universe, including eras before and during the formation of the first luminous objects. In principle, this signal could provide far more independent modes of information than the background. Instead of the one distant surface, it could offer layers across cosmic time. The practical difficulty is severe. Human radio transmissions, Earth's ionosphere, emission from our galaxy, and instrument systematics are all much stronger than the desired cosmological signal. Some frequency ranges may eventually be observed more cleanly from the far side of the Moon, shielded from terrestrial radio noise. If future instruments map primordial structure through neutral hydrogen, they may test inflation on scales not accessible through current surveys. Small variations in the initial spectrum, faint non-Gaussian correlations, or traces of exotic early processes could become measurable. Gravitational waves offer another path. The waves detected from merging black holes and neutron stars were created comparatively late in cosmic history. A primordial background would be different, a superposition of waves generated by processes in the early universe. Inflation may produce one such background. Phase transitions after inflation could produce another. Cosmic strings, if they exist, might generate a separate pattern. A bouncing universe could create its own spectrum. Different detectors respond to different frequencies. Ground-based interferometers measure rapid oscillations from compact object mergers. Space-based interferometers will be sensitive to lower frequencies. Pulsar timing arrays monitor the regular radio pulses of distant neutron stars, searching for even slower changes in the distance between Earth and those pulsars. No single instrument can hear the whole gravitational spectrum. A primordial signal may lie in one band, several bands, or below every planned sensitivity threshold. If detected, its shape across frequency could help identify the process that created it. A background from a phase transition might rise and fall around a characteristic frequency. Inflation could produce a broader spectrum. Cosmic strings might generate signals over a wide range. The interpretation would require comparison among several observatories and with the microwave sky. This is a recurring feature of cosmology. Confidence comes not from one measurement alone, but from different kinds of evidence meeting in the same physical picture. The temperature pattern of the microwave background can be compared with its polarization. Galaxy clustering can be compared with gravitational lensing. Light element abundances can be compared with the expansion rate inferred from early radiation. Gravitational waves may eventually add a record that traveled through matter almost unchanged. Each observation has its own sources of error. When several independent methods point toward the same early conditions, the shared explanation becomes harder to dismiss. Spatial curvature remains another important test. Inflation generally drives the observable universe toward flatness, but not always with perfect exactness. A sufficiently precise measurement of non-zero curvature could reveal how long inflation lasted or challenge certain models. The difficulty is that curvature can be confused with other cosmological parameters. Measurements rely on assumptions about dark energy, neutrino properties, and the growth of structure. Improved combinations of data may reduce these degeneracies. If the universe is exactly flat within every reachable precision, inflation remains compatible, but not uniquely confirmed. If a small curvature is detected, its sign and magnitude could provide a clue about the larger geometry beyond our horizon. That horizon defines a lasting limit. There are regions so distant that their light has not had time to reach us, and under accelerated expansion, some may never become visible. No improvement in telescope size can recover information that has never entered our observable domain. Cosmology must work with the part of the universe that can affect us. This does not make the effort small. The observable cosmos contains an immense number of independent regions, wavelengths, galaxies, and physical processes. Hidden in their statistical arrangement may be evidence from intervals shorter than any ordinary unit of human time. A detector cooled nearly to absolute zero may measure microwave photons released before any star existed. A survey may collect the redshifts of distant galaxies and recover the shape of fluctuations born far earlier. A radio antenna may listen for hydrogen from the first long night before galaxies filled the universe with light. The instruments are recent. The patterns they receive are not. Across generations, observers have learned to treat the sky as more than a collection of objects. A point of light can reveal a star's chemistry. A slight shift in wavelength can reveal motion. A faint distortion in a galaxy's shape can reveal unseen mass. The early universe extends this practice to the largest possible scale. There is no image of inflation waiting to be uncovered behind the microwave background. There are only relationships, one scale compared with another, one polarization direction set beside millions more, one theory asked to account for several relics at once. Through those relationships, the invisible past becomes constrained. The work does not bring the beginning close enough to touch. It does something more careful. It gives the darkness a measurable shape. There is a point in this story where the word before begins to change. In ordinary life, before is simple. One event ends, another follows. A room is dark before a lamp is lit. Winter comes before spring. The sequence rests on a clock that continues through both conditions. Near the earliest universe, that familiar order may not survive. General relativity describes it as part of space-time rather than a separate background flowing outside it. Matter and energy shape that space-time. and its geometry shapes the motion of matter and light. If the geometry itself reaches a boundary, then asking what happened earlier may require a theory in which time is still defined beyond that boundary. Inflation does not automatically provide one. It may describe an early interval of accelerated expansion, but most inflationary models begin with a spacetime already present and a field already occupying some condition. They tell us how one cosmic phase could evolve into another. They do not necessarily explain where the field, the laws, or the stage on which they act came from. This distinction is easy to lose because the earliest fractions of a second sound close to an absolute beginning. Yet moving the equations farther back is not the same as reaching the origin of everything. A model may say that inflation lasted for a certain interval before reheating. Another may place a contracting phase before inflation. A third may replace both with a quantum state from which classical spacetime emerged. Each possibility gives the word before a different physical meaning. The difficulty is not merely that the events are remote, it is that our usual concepts were formed inside a mature universe. We know heartbeat, a pendulum, the vibration of an atom, the rotation of a planet. Every clock depends on a physical process. To speak of time where no stable particles, atoms, or classical geometry exist is to rely on mathematics far beyond direct experience. Even so, the question is not meaningless. Physics can ask whether one state predicts another, whether a boundary is smooth or singular, whether information can pass through it, and whether measurable relics distinguish one history from another. The language becomes more careful, but the investigation remains scientific whenever the models produce consequences that observation could test. What science cannot do is turn every form of wonder into an equation. Why there are laws at all may not be the same kind of question as how a field evolved. Why anything exists may not yield to the same methods used to calculate the microwave spectrum. These questions can stand beside cosmology without being disguised as measurements. The edge between them is not a defeat, it is a boundary of method. For centuries, people looked upward and placed beginnings in stories, cycles, divine acts, fires, or voids. Those traditions carried meanings that belonged to the cultures that formed them. Modern cosmology asks a narrower question: which physical histories are consistent with the evidence available now? The narrower question has taken us far. From a faint microwave glow, scientists inferred a hot plasma that filled the young universe. From the abundance of light elements, they reconstructed nuclear reactions during the first minutes. From the arrangement of galaxies, they traced the growth of primordial density variations. From polarization and statistical correlations, they now test conditions that may reach back toward inflation. Each step replaces a portion of the unknown with a more constrained unknown. That phrase may sound modest, but it describes much of scientific progress. A mystery does not always vanish. Sometimes it becomes smaller, sharper, and more difficult to misunderstand. The history of cosmology is filled with such changes. The Milky Way was once treated as the whole universe. Then other galaxies extended the scale. The stars were once thought fixed. Then their motions became measurable. The cosmos was once assumed static. Then the expansion of space entered the evidence. The microwave background itself began as an unexpected radio signal and became a map of early structure. No generation received a final view. Each inherited a sky made more legible by the work of those before it. There is a generational thread in this kind of knowledge, though it rarely appears in equations. An instrument may operate for only a few years, but its measurements depend on ideas refined across decades. A detector built in one country may rely on materials, calibration methods, and mathematical tools developed elsewhere. A map of the ancient sky may carry the labor of thousands of people who never meet. The light they study has traveled almost the entire age of the universe. You can picture that light arriving now, not as a beam visible in a room, but as microwave photons entering a cooled detector. Their journey began before the first star. Their final interaction may produce a small electrical signal, which becomes a number, then part of a map, then a test of a model about the beginning. The distance between those moments is nearly the history of everything we know, and still the interpretation must remain restrained. A successful model is not a memory recovered from nature. It is a structure that explains evidence and survives attempts to disprove it. Inflation may be the correct description of the early universe. It may be an approximation within a deeper theory, or a different mechanism may eventually account for the same observations more convincingly. The answer will not be chosen because one story feels more complete. It will be chosen, as far as possible, by the traces each story predicts. This patience can be difficult because beginnings invite certainty. They seem to promise a final explanation from which every later event follows. But cosmology may never offer a single sentence in which the universe becomes fully accounted for. A deeper theory may explain inflation and leave its own constants unexplained. A quantum theory of space-time may remove the singularity while opening new questions about its boundary conditions. A cyclic model may extend time indefinitely and still require an account of why cycles have the properties they do. Explanation can move backward without reaching a final flaw. There is no reason this should diminish the value of what has been learned. Knowing that the universe was once hot enough to prevent atoms is not made less meaningful because reheating remains uncertain. Knowing that galaxies grew from early density variations does not depend on possessing a complete theory of quantum gravity. Knowledge can be real without being total. Cosmology applies that humility across the largest possible canvas. Tonight, the observable universe contains stars that formed recently and photons that have traveled since matter first became transparent. It contains black holes, cold gas, planets, dust, and living observers capable of asking what preceded all of them. Those observers are not outside the story. The atoms in their instruments came from stars. The gravity holding their planet formed structure from the same early fluctuations they are trying to measure. Their thoughts depend on matter that survived the first annihilations and was assembled through billions of years of cosmic evolution. The universe is examining its own earlier conditions through one of the structures those conditions allowed. This does not grant humanity a special location in space. It reveals a continuity. The quantum fluctuations considered in inflationary theory are not separate from the present cosmos. If the theory is right, they became part of the distribution from which galaxies formed. The early plasma became the material of stars. The first nuclei became ingredients for later chemistry. The ancient expansion continues in the increasing distance between unbound galaxies. The beginning is not a vanished place. Its consequences are active everywhere. They are present in the near flatness of space, in the proportions of hydrogen and helium, in the background radiation passing through your surroundings, and in the large-scale arrangement of galaxies beyond sight. What lies before the oldest light may remain invisible, but it is not detached from the present moment. It is folded into the conditions that made the present possible. And perhaps this is the most grounded way to approach the hidden beginning, not as a remote spectacle, but as a set of early conditions still unfolding through matter, distance, and time. The universe before visibility did not leave us a portrait, it left us consequences. The oldest visible light still crosses the universe. It moves through galaxy clusters, dark matter halos, intergalactic gas, and the changing geometry of space. Some of it is deflected, some is absorbed. Most continues, carrying the pattern imprinted when atoms first formed and the cosmic fog became transparent. By the time that radiation reaches a detector on Earth, the universe has changed almost beyond recognition. The plasma has become galaxies. The first density variations have grown into clusters and filaments. Hydrogen has passed through stars and returned as heavier elements. Planets have assembled from debris around later generations of suns, yet the microwave background remains. Its temperature has fallen as space expanded. Its wavelengths have stretched from the glow of a hot young cosmos into the microwave band. The radiation has become colder and fainter, but its pattern still links the present universe to conditions near the beginning, the hidden era before it approached through that connection. Inflation may have carried microscopic fluctuations outward until they became the seeds of structure. It may have smoothed curvature, joined regions that now appear causally distant, and prepared the hot state from which familiar cosmic history emerged. These ideas remain powerful because they explain several observations together. They remain incomplete because the mechanism has not been identified. No confirmed particle has been recognized as the inflaton. No direct relic has yet revealed the energy scale of inflation. No observation has settled whether inflation began after an earlier phase, arose from a quantum boundary, or belongs within a history much larger than the observable universe. The evidence does not lead to a clear image of a first moment. It leads to limits. The early universe was hot and dense. Its matter and radiation were once closely coupled. Its light elements formed during the first minutes. Its oldest visible radiation was released hundreds of thousands of years later. Its initial density pattern was nearly scale invariant, nearly Gaussian, and remarkably simple. Any successful account of the hidden beginning must pass through those facts. Inflation does so well. Alternative models must do the same. Future measurements may sharpen the difference. A primordial gravitational wave signal could reveal a scale of energy far beyond present experiments. A subtle non-Gaussian pattern could expose additional fields or interactions. A departure from flatness could constrain how long inflation lasted. A 21-centimeter map could uncover primordial information across volumes that the microwave background cannot provide, or the next generation of instruments may find no new trace. That would also change the theory. Some models would disappear, others would retreat toward weaker effects. The space of possible histories would become narrower even without a dramatic detection. This is how knowledge advances at the edge of observation, not through certainty arriving all at once, but through possibilities losing room to hide. The universe before visibility may never become visible in the ordinary sense. There may be no picture waiting beyond the surface of last scattering, no preserved beam from inflation that can be focused into an image. But visibility is not the only form of evidence. A pattern can survive where an image cannot. Geometry can preserve a history. Statistics can carry the influence of events too early for light to describe directly. The sky is filled with these indirect records. A galaxy's position reflects the growth of earlier density variations. A cloud of hydrogen carries the outcome of primordial nucleosynthesis. A faint polarization pattern may contain the effect of waves in space-time. The proportions of matter and antimatter reveal that some imbalance arose before atoms existed, even though its cause remains unknown. Every observation reaches backward by following consequences, and every consequence arrives in the present. There is no need to imagine yourself standing outside the universe, looking down upon its beginning. No such viewpoint exists within the science. The early cosmos was not a distant object surrounded by emptiness. It was the earlier state of all the space that would later contain observers, telescopes, and the questions they ask. The place where you are now was included in that history, not as a planet or a location with a name, but as part of the same expanding geometry. The matter nearby was once distributed through hotter and denser forms. The background radiation passing through this room began its free journey before Earth, the Sun, or the Milky Way had taken their present shape. The beginning is far away in time, but it is not elsewhere. This is why every direction leads toward the same ancient glow. Look north, south, east, or west, and the microwave background appears behind the later structures of the universe. Its near uniformity surrounds every observer because every observer exists within the same expanding history. There is no privileged center from which the Big Bang spread outward. Expansion occurred throughout space. The early plasma was everywhere. The release of the oldest light happened everywhere. The hidden era before it belongs to the past of every region we can see. This removes one of the most persistent images from the story. The universe was not a small object exploding into a larger darkness. The observable region was once much hotter, denser, and more compact, while space itself evolved. Inflation, if it occurred, was not motion away from a central point. It was a change in scale woven into the geometry of the cosmos. The mathematics can describe that change with remarkable economy. The physical meaning remains deeper than the equations alone. A field may have held nearly constant energy while space multiplied. Quantum variations may have crossed a horizon and become classical patterns. Reheating may have converted field energy into particles. Matter may have survived annihilation by a slight excess. Gravity may have followed those differences for billions of years until stars and galaxies appeared. Each step carries uncertainty in different measure. The uncertainty is part of the map. It tells us where observation is strong, where inference is persuasive, and where theory still travels without confirmation. It prevents a possible history from being mistaken for a recorded one. The universe does not become less beautiful when the limits are named. It becomes more precise. There is a kind of calm in that precision. The beginning does not need to be forced into certainty. The evidence can remain incomplete without becoming meaningless. A question can stay open while the boundaries around it grow clearer. For now, inflation stands as a leading explanation for why the observable universe began so smooth, and yet contained the slight differences required for structure. It connects quantum physics with galaxies across a scale that no laboratory can reproduce. Whether it is the final description is unknown. The next clue may come from polarization, gravitational waves, galaxy surveys, or a method not yet invented. It may confirm a simple model, point toward a more complicated one, or reveal that the early universe followed a path not presently imagined. Until then, the oldest visible light continues to arrive. It carries no final statement about what came before. It carries a pattern shaped by what came before. And that pattern is enough to keep the question open. Beyond the first transparent moment, the universe remains hidden. But even hidden beginnings leave a direction in the light.